Okay, so let's look at some examples of these graphs and see if it says if it tells us anything interesting. Okay. So as just sort of like, let's just look at this as a basic example. I don't know which, I don't remember which example number one. What did I show last time? I showed those guys. Okay, maybe I'll just start by redrawing those. Okay, so and maybe I'll undo my mistake of not drawing them in the shadow diagram. So the easiest way to see the graph of the spine is, well, is to consider a shadow diagram, which is sort of naturally a picture of the graph.
You mean take 3 color more.
Pardon?
Take 3 color more. Every cubic take 3 color more.
I thought a 3-edge coloring is what's known as a take color.
Oh, I see.
Yeah.
Right now, sorry.
I don't know. You know, based on what I read on Wikipedia.
Right.
Yeah, edge 3 colorable. Yeah. Okay. Couple of graphs here. And let's see. This. Okay, so this is one graph. So this is a, let's see, what is this? This is a 4-1, I think. Yeah, 4-1 shadow diagram for the surface P21, or they both are. In fact, this one will be once I draw the reflex on. So this one, I guess, similar as I can. Okay, this guy. Yeah, I think that does it. Okay, so these are both shadow diagrams for bridge trisections of the same sort for the same surface. But these two bridge trisections are distinguished by the fact that this one, the first one, contains a copy of K33 as a minor. So you can think of this by contracting maybe these two edges and deleting this green edge, and then you'll end up with the utility graph. And this one is planar. Okay, so they're definitely different graphs, which means there's at least 2 bridge trisections for this surface, 2 distinct bridge trisections for this surface. And the other thing I pointed out last time is that a triangle in the graph is prescribing an RP2 summand, or a P plus or minus summand, because we can draw this reducing curve. And so in particular, these are both reducible. And reducibility of the bridge trisection, I think, is very easy to read off from the shadow diagram, because either you can find a curve that intersects in only 3 edges, or you can't. Well, I guess that could be.
Well, you might not. You might have to do a bunch of jumps first. No.
Is that right? Yeah, maybe that's right. Yeah, maybe it's not so obvious. Sorry. Right. Okay, I think I wanted to say something a little bit different. So maybe as the next example, I'll just say that there are 2 irreducible bridge trisections. These are 5-1 bridge trisections for the connected sum of 4 copies of RP2. And I haven't checked whether or not these can be made to have the same Euler number or not. So maybe this is actually not so interesting in that, well, if they can be made to have the same Euler number, that's sort of interesting because there's 2. So let's make that a question. The same, you know, let's see, are these both? Let's see that. Can these be made to have the same Euler number in any way? But even if they can't, and we're really just picking up 2 different versions, you know, maybe we're picking out P22 and P31, right? Or even I guess P40 or any of the mirrors of these guys. It's still interesting that these are irreducible because up to 4 bridge there are no irreducible ones at this point. And by that I mean, sorry. I think what I meant to say is it's straightforward to check whether or not the graph is reducible as an abstract graph, right? So you have to be a little bit careful to separate the embedding information that's inherent in the bridge trisection with just the fact that for the moment we're just talking about abstract graphs.
But the point is you can obstruct embedded reducibility by obstructing abstract reducibility.
Exactly. So yeah, so let me draw one of these examples. Maybe you'll believe me. All right. You're very trusting people, so you probably already believe me. Okay. All right, so let's see, I drew these as, let's see if I can do this. I'm just gonna draw it like that, and I'm gonna try and fix it. Well, maybe I won't even bother, since I really just want to think of this as an abstract graph. Okay. So this is one of the abstract graphs coming from, well, this is an abstract graph that is cubic and admits a 3-coloring, and the oil, you know, you can calculate the homeomorphism type of the surface by capping off the circuits formed by pairs of curves with this. I think you talked about abstract surface trisections a little bit. Okay. And this graph, I claim it's, I don't know. Maybe I'm a little less confident about this now, but I claim that if this were reducible, we would be able to find a, you know, if nothing else thinking it was a spatial graph in 3 space, we'd be able to find a sphere that separated off that intersected the graph in 3 arcs, 1 of each color. If that's, I guess, what I define reducible. And yeah, I guess maybe I shouldn't say too much more about that. But I think sort of in the same way that you can tell from an alternating link diagram whether the link is a connected sum. You should just be able to look for curves here that are intersecting and simple closed curves that separate the vertices. Does that seem right? What do you think? Do you believe?
Well, and if it's abstract, you really just need 3 dots. I mean, if you think about your wiggly thing over there, right? It's just set. It's really just you cut.
Oh, 3 cut. Oh, like a cut. 3 edges. So 1 edge of each color that's like a cut.
Yeah.
And
if that becomes like
that's a checkable.
Yeah.
Okay. All right. Yeah. So I guess that's okay. That's good. So then we can verify then this is irreducible, which is great. So we see that at least at some point these things start being irreducible. Okay. And let's see. I think I had.
Can I ask a question?
Yeah, please.
So, sorry, I might have missed something. Are they supposed to be the same graphs from last time? Or
Yeah.
I think they're different. But I don't know if it matters.
No, that's okay. They may look different.
They might be like, yeah, they might be the same as graphs?
They're the same as
You
graphs.
moved all the green arcs so they don't
No.
intersect each other.
I might have actually changed the coloring of the graph. See here, I have 4 graphs.
So we probably showed this up.
This one is the one that's, this one's the one that's different, right? Oh, you showed this in your summer
We
thing?
might have. I don't
Yeah,
know.
you might have, yeah, that's right. Yeah, I may have switched the
Oh,
color.
that's right, this is the high school.
Yeah.
So one cool thing about this, one cool thing about this program is if you restrict to the case where C1 is 1, you're just looking at this sort of red-blue cycle around the outside, and you're looking at these chords. So there's this whole theory of these sort of chord diagrams for graphs, and Gauss diagrams, and that kind of stuff. But the problem is sometimes you have 2 different chord diagrams that give the same graph. And so this chord diagram may be different from the one I did last time. But if you sort of interchange 2 of the colors, or maybe you cycle the colors or something.
I'll look back at my notes.
And so that, I guess I didn't really mention that explicitly here, but you can ask whether every graph type is realized as a bridge trisection, and you can ask whether every coloring of every graph is realized. Okay, let me give another example to drive home why that's an interesting distinction. So let me draw some graphs here. And all of this is basically just like the upshot of a few weeks of investigation over the summer, trying to figure out what happens with these little graphs. Or maybe, well, you guys had a little group that worked on this in the high school program for high school math students over the summer. Did you guys prove anything interesting?
I think so.
You think so?
I don't remember what.
There were various questions. Okay, let me concentrate on this. Okay. I'm not done yet, but red and blue are already different, right? Okay, so here's a cool graph. This is a cube graph. Is that what it's called? The cube graph. But 2 different colorings. And you'll notice the red and blue over here, would have been easier to notice before I drew the green, has 2 cycles. The red and the blue over there had only 1 cycle. And in fact, this is a 4-2. Maybe I'll just use a notation called a 4-2 graph, meaning that each bicolored cycle is 2 components. And this one is 4-1-2-1 graph. So the same graph has 2 different colorings, and it gives 2 different homeomorphism types of surfaces when they're bridge trisected. So I think that's kind of cool. I think that's kind of, maybe I'll add one more to this example, and then we'll be done. Let's see this. Okay, I guess this is a kind of a new example because it's not even the same type of graph, but we can compare these 2 because this is also a 4-2 graph. So both this and this give rise to 4-bridge spheres, but they can be sort of distinguished by their graph type just right off the bat. Great. So I think that's more or less all I have to say coherently about this graph stuff, but it seems like it's warrants a little bit of an investigation.
A question,
Yeah.
2-part question. So what's really yellow there, like that can't be P22 because where the characteristic is -2.
This just means 2 copies of one cross cap and 2 copies of the other. No, the other characteristic here is
Well, it's
minus.
-5-1. Don't you have 3?
Oh, did I get the things wrong? Are there oh, hold on, I see. Maybe you're right. Euler characteristic here is 3 minus 5, okay, is -2, I'm sorry. That's right, that should only be 3 copies of our control.
Previous version was P11.
Yeah, pardon?
That one, number, example number 4.
Oh, so is that where my problem goes back to here already?
Wait,
Wait.
2 minus 4 is -2.
Hold on, this is,
True statement.
what?
3 minus 4 is -2, so I think that was fine. I got mixed up about Euler here, Euler characteristic. But,
Wait, is everything right?
no, that's fine.
Everything's
I was
right.
mixing up
You tricked me.
Euler number and Euler characteristic.
Yeah.
Okay, so my question, the topology of the surface, the homomorphism type, give you a bound on the grid number. Like, if you have 4 RB2s,
What gives you a lower bound on the bridge number?
what is the lower bound?
Well, it's coming from Euler characteristic because Euler characteristic is,
Minus 2.
the sum of the C's minus B,
Right.
and the C's can only go down to 1.
Yeah.
And so, for example, if I wanted 7 of these, I would need to drive up B because I can't have a smaller C.
RB2s, it's at least 1 more than the number of them.
Yeah, so let's just see. I mean, so the smallest bridge,
That would be a different proof if that's irreducible, right?
hold on. Is that your third
What
question?
does irreducible mean?
Irreducible means not a connected sum.
All right.
It does not mean not perturbed. Which is what you're thinking?
Yeah, that's what I was thinking.
Okay, part 10. Did I answer all your questions?
Yes.
I didn't answer your question about the lower bound, but that's an exercise. All right. Okay. Perturbation and and we can keep a running total of how many times I say stabilization instead of perturbation. All right, so what I'd like to describe for you now is a process that you can take a bridge trisection and you can perturb it to get of a surface, you can perturb it to get a new bridge trisection of another surface with higher complexity. And then we'll write down a theorem that says by doing this process and its inverse some number of times, you can get between any 2 bridge trisections of a given surface. Okay, so let's spell this out. So let's start with a bridge trisection, I guess I'll call it T, of some surface S and S4. We have the following. Natural procedure to get a B prime, C prime bridge trisection, T prime for S, which satisfies B prime equals B plus 1, and C sub I E prime equals C sub I plus 1, and C sub I plus 1 equals C sub I plus 1 prime on the first one, and C sub I plus 2 prime equals C sub I plus 2. So that would be like unintelligible if you're speaking it into your iPhone, but written it doesn't look so bad.
That's probably true for most math, but.
That's true, yeah. All right, Siri doesn't understand subscripts. Yeah, somebody should implement the math jacks in messages. That would actually be very useful for me because I'm always texting my co-authors stuff. Okay, so what is this procedure going to look like? Well, let's kind of draw some pictures. Try to illustrate it. Might be a surprise. Okay, so let's think about our triplane, and then deviate from my notes here. Let's pick a nice hybrid example. Okay, so let's see, where should I put my steps? All right, so step one is to choose a disk D inside the ith disk tangle, comma, and isotope it to lie in the boundary three manifold Yi, which we can do since it's trivial, as a disk, which I'll denote D star, and we'll let J denote the boundary of D, which is also the boundary of D star, and let B sub J be the bridge number of J, or the bridge index, I guess I would go ahead and say. Maybe that's not a bridge index of J with respect to the bridge surface sigma. And then the last thing I'll say is, without loss of generality, we'll assume that E star is vertical. I don't know if I want to be super precise by what I mean now, but let's just look at this. So, okay, so there's this disk there's this disk in the four-dimensional, see if I can draw this. There's a sort of disk, kind of do these little weird things. So there's this disk D star lying out here in the sector Z sub I, and we want to push it. I'm just going to redraw this picture again many times. We want to push it to lie in the boundary. So I've sort of taken the so you can kind of see what I mean by vertical here. I mean, there's an obvious Morse function coming from the bridge splitting of Yi given by sigma. This is Yi, this is sigma. And you can ask that the disk has no critical points in its interior. You can also, it's also probably just enough to ask that it intersects the bridge sphere in only arcs, no simple closed curves. I think that would probably suffice for what I want. Okay. So step one is to sort of choose this was D. Choose this disk out here in this disk tangle and push it in. And so I'm going to just draw the boundary as that. Although you could imagine braiding this disk up, keeping it vertical but braiding it up. That would be fine too. Okay, so step two is to choose an arc omega delta inside D star with one endpoint on each tangle. So the tangles in this case are Ti and Ti plus 1, such that D intersects sigma is a point. So we want a vertical arc basically, going from somewhere on the red tangle somewhere on the blue. So maybe I choose this one right here. This is my delta. Okay. And maybe actually this guy should be called delta star. Never a good idea to change notation off of that. Okay, so let's just make an aside. I can pull delta star back to an arc delta inside the disk D, inside the disk tangle inside the interior of Z1, using this boundary parallel 3-ball. Right, there was a 3-ball that I used to push D in, and if I pull this out, I get something that's like this. Okay, so maybe I draw it inside here. So out here I have delta, and in here I have delta star. And together they co-bound this triangle, which maybe I'll call capital delta. So there's a triangle, delta, inside the membrane for D, such that the boundary of this triangle is delta union delta star. Okay, so this is the setup that we'll need for this perturbation. Okay, and the next thing we do, I guess this is still part of 2. Let's let B be a neighborhood of delta star inside the disk D star. Okay, so we're actually going to take a band neighborhood of delta star, and we could pull that back to band neighborhoods of this whole setup. Okay, that's the band B. All right. Any questions about the setup so far? Okay. And so now we're going to do our perturbation. So what we do is we push the interior of the band into the other side. So this is zi plus 1 union zi plus 2. Okay, so we have this band sitting in yi. Yi is separating zi from the other z's, and we're going to push the interior of the band into the other side. And then the other thing we're going to do is we're going to push the interior of d star minus the band back into okay. So that's just like returning d star to d, except not with this region of delta. So another way to think of this is we have this triangle delta, and what we're doing is like a karate chop or a Whitney move along this delta, and we're taking this disk and our disk tangle, and we're karate chopping it so that sort of the slice of it pokes through into the other side of our trisected S4. Okay. So let's see what happens. Draw a couple of pictures. So what does this look like in this picture? So I've drawn a more exaggerated version. And then something that I had neglected up to this point is to draw what's happening on the backside. Well, locally, we just see little pieces of our third tangle flying off. And if you think about what's happening is we're taking this arc and we're doing the band resolution along this band B. So maybe I can draw it like this. Something like that. That's what it looks like when we push this interior of the band out of this sector and onto the other side. And what happens on the back side is it sort of just bends through like that. So let's actually draw what the back looks like. So the back, before we did anything, I'll just draw sort of a, let's see, local picture of the back. Something like this. No, that's not very clear. Let's make it Might as well draw the whole thing. Okay, so on the back, we just had some green stuff like this. And if you think about what the sort of like disk system in between, red plus green makes orange. So this, we sort of have this disk system that locally kind of looks like these tents. These little tents, little tunnels. And up here we have a big tunnel, right? Really direct this. Okay. So the surface is just kind of going out like that in this sector, which I guess is probably zi minus 1 or plus 2. And then what happens when we do this stabilization is,
Call it stabilization instead of perturbation.
is that the first time?
That's the first time.
Good thing. What happens when we do this perturbation is, oops, we do something that sort of looks like this. So again, this is overpass. Oh, but now this thing, now it's kind of dimples. You get like this tube here inside. So the dimples. Something like that. So all we've really done is we've taken this, oh, and it was supposed to be orange. The regrets in life. We've really just taken this orange disc and sort of just nudged it. You know, the end of our karate chop just kind of poked it a little bit to create this little tunnely dimple here. Okay. And so, you know, if this was di plus 2, then now what we have here is a new disk system, di plus 2 prime. And it's clearly a trivial disk system of the exact same number of patches. You can think about kind of all we did with this disk is we kind of just took this part of this and kind of just nudged it down like this. Like if you stuck your fingers here and went down and like that, around in the boundary. So it's almost like a boundary isotopy, you know, still a trivial disk system. Same thing. So let's just observe. So di plus 1 prime and di plus 2 prime are trivial ci plus 1, ci plus 2 disk tangles. Still. So that's good. I guess we, and I didn't really finish talking about what happens in the primary sector here. Well, we've really just cut a trivial disk into two trivial disks. And because we did it in the boundary, the result is still going to be boundary parallel. So maybe we call this d star 1. That's not confusing at all. And d star 2. And what we see is that the disk tangle d sub I goes to a new disk tangle d sub I prime, which we can think of as d sub I minus d union d1 union d2. Where those are the push-ins of these guys. So the three pieces are all trivial disk systems. So it is d sub I prime. But notice this one is, sorry, d sub I prime is a c sub I plus 1 trivial disk tangle. Okay, so the complexity of that piece has increased by 1 because we split it into 2. All right. Okay. And then now what about the tangles? Well, the third tangle, maybe I'll just stay over here. Ti plus 2 just goes to Ti plus 2 prime, which is now it's b plus 1 bridge trivial tangle, and it's still trivial. Because all we've done is we've added a little boundary parallel arc. Okay. You can sort of always add a little boundary parallel arc. And then, let's see. And same thing is going on here. This we can actually just sort of explicitly see both of these tangles are still going to be true because we essentially, what do I want to say here? Let's see. So, why is this still showing up? Okay, so I think this is what I want to say. So for this tangle, we could have chosen the arc. So the arc delta, where it coincides with one half of it, we can choose to lie in a bridge disk. So in that case, we're just splitting a bridge disk or a membrane into two. And in this one, we could isotope this back membrane for the big red guy so that it coincides with the arc along this vertical piece. And there we also, so in both cases, you can arrange things so that when you do this sort of banding, you're just sort of splitting a membrane on each side into two membranes. So I think that's probably okay. Okay, and so I think that's what I want to say. So so I guess the lemma is that this new bridge trisection is a C prime, C bar prime bridge trisection. And it's for the same surface because all we did is isotope the surface locally in this sort of three ball that's right near the spinal bridge of the trisection. Okay, and so we call this, let me just make it all. I think for brevity, I'll just, instead of rewriting it, I'll put an I in front of it. We call this I perturbation. Okay. So note that there are three directions to perturb, right? That this perturbation affected the complexity of our bridge trisection asymmetrically. It changed one of the disk systems, but not the other. Moreover, this depends on a couple choices we made. It depends on the choice of D inside the disk tangle, and it also depends on the choice of delta inside the flat disk, the disk shadow. Okay. And you can see that here, in this example, I took a 4-bridge component. So B sub j was 4, or B sub j. The bridge number of this boundary was 4, and then I split it so that the result is 4. Right? I split it so that the result is 3 and 2. Okay? But you could have also split it, if I had done this here, I would have split it so that the result was 4 and 1. Okay, so you can get different partitions of 5. Or different partitions of B sub j plus 1, depending on which vertical arc you choose. Of course, there's sort of only, B sub j minus 1 choices. This is B sub j minus 1 choices, because there's only so many vertical arcs in this vertical disk. And I guess there's only C sub I choices for which flat disk to use. Okay. 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 So I don't think I'm going to get to everything I wanted to say in the last 5 minutes, but I'll start with most important or least important. So theorem is that any two bridge trisections for a given surface length can be related by a sequence of perturbations and deperturbations. So what is a deperturbation? Well, a deperturbation is where you do the opposite.
The phrase can be related.
Can really become isotopic, yeah. Become isotopic after. That's a better way to say it. Become isotopic after. And so a big question is, it would be this. Do any such two bridge trisections have a common perturbation? So this is a sort of a Reidemeister-Singer type theorem in that it says these two sort of more theoretic structures can be related by perturbation, deperturbation. But in other statements of Reidemeister-Singer, so for example, with Hegardt splittings and bridge splittings, you have a result where you just have to perturb this one and perturb this one enough times that they become isotopic. Here, so that would look something like this, right? You perturb some number of times. Maybe they start at different levels. But here what we have is we go up, and then we go down and up and down, down. Maybe we go down to there, up, and so on. So it may be possible that you need to perturb, then deperturb, then perturb, then deperturb. And the way we prove this is, if you think back to the moves on banded links, we have these slides and spins and stuff. We basically promote those to moves on banded bridge splittings, and show that each slide, for example, can be realized through a sequence of banded bridge splittings where we may need to be stabilizing the banded bridge splitting, perturbing the banded bridge splitting, and deperturbing it along the way in order to execute the slide. So,
I mean, if I wanted to try and prove this, I would just simplest thing would be trying to show that if I have a perturbation after a deperturbation, I could have done it before. Right? If you perturb after deperturbing, it'll show that you could have perturbed first and deperturbed afterwards. And do you have a prototype example where that?
yeah, so if you look at the details of the proof, I mean, when you do a handle slide, you need to perturb it until it's in a nice position, and you need to then, let's see. So
Why would you need to deperturb before perturbing? That's
before perturbing,
That's
right. What is the easiest?
if it's not even.
Yeah, I guess
If it takes too much time, don't do it now.
well, we can't take too much time over that. But actually, since we're going to next time, maybe that would be a good thing to talk about next time. I'll give an example of how you need to do a sequence of perturbations and deperturbations to do a handle slide, or to do a band slide. Yeah, I don't think I can do that one. Oh yeah, so one way you could, so I claim that you're not going to be able to answer this question using the same proof that Alex and I did. But what you might try to do is prove uniqueness some other way. So maybe a natural question is there a Morse 2 function proof of this uniqueness of a common stabilization? So I don't know, this seems really difficult. But it also seems like if you could prove a uniqueness result in this way, it would be that you can do all of the stabilizations. But it's hard to believe from if you were doing some sort of Morse 2 thing, why you would need to perturb and then deperturb. I even wrote it, that counts to like -5. Okay. So, all right, I think that's probably good for today. Next time we'll just have a few comments about like what these things, what do perturbations and deperturbations look like in, say, shadow diagrams? Why do we need to go up and down, up and down, up and down? But I think we'll end now since I usually go over. All right, any questions?